Okay, so now we're switching over to the topic for today, which is what optics are there available. So we have this radiation coming out of the synchrotron or the free electron laser. We need to get it onto our sample. Maybe we want to focus it to a small spot of so many nanometers. Almost all beamlines at synchrotrons or FELs use optics in some manner. So what are the choices of optics? One is there are glancing incidence reflections. So you have some mirror material, okay, maybe just silicon or copper or something like that. And you have X-rays that come and they reflect off the front surface. We call this total external reflection. We're going to talk about refractive index. The refractive index for X-rays is different than visible light. It's a little bit less than unity, and it has an absorptive part, which is important for all of the X-ray wavelengths. So for instance, the refractive index I'd mentioned before, for visible light, the refractive index, let's say going through glass or something like that, or water, the refractive index is something like 1.5. It's 1 plus something. Okay? For X-rays, it's 1 minus something. For visible light, you have total internal reflection. For X-rays, you have total external reflection. So for X-rays, if you just come down onto a surface, it's just going to get absorbed. Nothing good is going to happen. At glancing incidence, though, for X-rays, you can get a reflection. The glancing incidence angle, however, is small. It could be less than a degree for hard X-rays, a few degrees for soft X-rays. But anyway, it is a very, very common, it is almost every beamline we use this. For instance, light comes out, X-rays come out of this undulator, and we don't have one group working 24 hours a day. We have maybe a couple of different groups, and there's a mirror that deflects the beam to one side or the other side, and it's just using this glancing incidence reflection, just a flat mirror. If the mirror is curved a little bit, there could be some focusing in this direction, and if you have two mirrors, not flat, but they're both curved, one is focusing a little bit in this direction, the other one has curvature this way, focusing in the other direction. That combination of two curved mirrors is called a Kirkpatrick-Baez mirror pair, generally KB mirror pair. It's named after Paul Kirkpatrick and Albert Baez, who worked together on this. Has anybody heard of the American folk singer, Joan Baez? Anyone? Nobody. Oh yeah, okay. Yeah. It's an age thing. And she was very famous in the Vietnam War. Okay, she was against the war, and she sang and she played her guitar and everything else. And Al Baez, his name is Al Baez, but he said, I gave up after a while because his daughter was so famous, all his friends started calling him Baez also. So he became Baez. And Kirkpatrick, I had invited him to a seminar, a conference. He was like 90 years old. My heart dropped. He was on a stage. When he was done talking, he jumped off the stage. The guy was 90 years old, and the stage was like this high. But somebody in the audience asked Kirkpatrick, who was your best student? And there were several of his former students sitting in the audience. But this guy, 90 years old, boy, was he sharp. He said, oh, that's easy. It was Joni. I taught her to play the guitar. So anyway, so that's the KB microscope. There are also interference coatings where we call them multilayer or multilayer interference coating or some kind of multilayer mirrors, ML, okay? Where it's like an artificial crystal, except it's amorphous in the planes, and as light or X-rays come in, there's a reflection at each interface, and they add up in phase. And so at long wavelengths, even at X-ray wavelengths, soft X-ray, you can get a much better reflection this way than you could from a single surface, okay? And in fact, I'm going to show you one if I get time at the very end. In the extreme ultraviolet, just below the silicon L edge, there's a molybdenum-silicon, molysilicon mirror. You can, even at normal incidence, you can get a very high reflectance, up to 70%. At 92 eV, below the silicon edge at 99. And the wavelength is 13 or 13.5 nanometer. It's what I mentioned to you is used for making the latest, greatest computer chips. So I'll come back to that probably briefly at the end. The other thing is, this is a transmission grating, which you probably learned about in high school physics, okay? There's some opaque regions, there's a wavelength coming in, and there's a diffraction pattern, and you figure out the angle at which these things add up by having them, the path lengths all increasing by one wavelength, right? Constructive interference. And the closer these things are, the bigger the angle is, okay, the diffraction angle. So now you're ready to understand the zone plate. Zone plate is a circular diffraction pattern, and the closer zones on the outside produce a bigger deflection. The inner zones are a little bit longer in period, and the angle, the resulting angle is a little bit less, and you can get a real focus. So you can use this for focusing radiation, you can use it as the lens in a microscope, and so I'll show you a little bit about that in a moment. In general, refraction doesn't work because of absorption, but at hard enough X-rays, you can have a refractive lens. This looks odd because normally you would have a convex lens like this to focus X-rays, but that's because the refractive index would be positive. So because of the negative part of the refraction, this thing produces real focusing, okay? Probably has a lot of absorption. So, but at, let's say 10 or 20, at 10 keV X-rays, this will focus in the proper direction, and you can minimize absorption by using something like beryllium, maybe even aluminum, but beryllium would be really good. And if you put a whole bunch of these together, it's a kind of a weak focusing, but if you put a lot of them together, that's what this is. It's called a compound. This is a refractive lens. This is a compound refractive lens. And if you look here, this part right in here looks like that. It's closer here and further outside. And so this is a sequence of these, and you can have hundreds of them. And this was invented by a husband-wife team here at ESRF, Anatoly and Irina Snigarev. So many people just call it a Snigarev lens, okay? And they're quite commonly used, even for just alignment of photon beams at hard X-ray facilities. So this is the array of optics that we use, and by the way, including the pinhole. Does someone want to ask a question or just say something? Yeah.
Yeah, so just for the orders of magnitude, since I'm a neutron guy, I wonder how you're talking about absorption. How much does, for example, 1 centimeter of aluminum absorb X-rays? I have no idea if it's 10% or 90%.
So for soft X-rays, what was the distance you chose? A centimeter?
For example, centimeter, but
yeah, yeah, no, it's good. So a centimeter of aluminum, no soft X-rays are going to get through, right? It's going to be 10 to the minus a lot. But for, let's say, for 30 kilovolt X-rays, a lot would get through.
Okay.
Yeah. I think I'll probably have a transmission curve at some point here.
Okay.
Well, this just says what I've already told you. This is the KB system, by the way, the two curved mirrors. And now, what about the refractive index? Why does this refractive index a little bit less than unity, but not much less? So this is an expression, some epsilon 0. This is an expression for the refractive index as a function of frequency. You can put h bars on these and it'll become photon energy. This is a semi-classical description. So you could use this for visible, etc. Works for X-rays also. It doesn't work if you're right on center for some narrow frequency, but basically we use this. This is the expression that we generally use for refractive index across the spectrum. So this would be for some frequency of omega, and this is if you characterize your atom as having a bunch of resonances. So these would be the energy differences between n equals 2 and n equals 3 levels of your atom. So these are the resonances that exist within the atom, and the refractive index depends on these things. So It's the difference between the frequency and the resonance. So if you write on resonance, that's where this formula fails. Okay, if you're exactly at the resonance. But generally, we're not exactly at the resonance, and this is quite useful to us. And this is a sum over all the resonances. So you know you have an initial state and the final state. So if you wrote this quantum mechanically, it would look exactly the same, except you would sum over resonances ij, initial states and final states. Okay? And there's an absorptive part in here. This is a different gamma. This is an absorptive gamma. And this is an oscillator strength. Of all the different transitions that you might have, this would be, I just put an S here, but this would also be an ij kind of thing. Okay? This is the atomic density. This is epsilon 0m. This actually has the units of a frequency. It's the plasma frequency. Okay? So if you were in the visible region, you're looking at green light, for instance, and you're looking at glass, the resonances are at a frequency higher than the green light frequency. So the green light is like maybe 2 eV, photon energy, to put this H bars on this, and this might be, it's higher photon energies. I don't remember exactly, but something like 9 or 10 eV. But at any rate, for green light, this is less than this. This one's less. So this minus sign cancels this, and you get a 1 plus. For frequencies where the frequency is less than the resonance, this becomes a plus. Okay, so for visible light, you're getting 1 plus something or other, and you have to account for all the different resonances. For X-rays, the frequency is going to be higher than some of the resonances, and so because it's higher, this is going to be a minus sign. Right? This is positive, so you're still going to have 1 minus something. So for X-rays where this is greater than this, you're going to get 1 minus something. But also for X-rays, these frequencies are so high that this collective number is small. So it's 1 minus a small number. Okay? A different way of expressing these things is in terms of, put all of this in terms of what's called oscillator strains. For those of you who are familiar with it, it's a complex oscillator strength. And these are the kind of things you can look up in those websites I told you about. Generally, if you want to read about this, there's a chapter. I think I posted it. If I didn't, send me an email and I'll send you whatever chapters you need. But this is kind of a lot to carry around. So we usually just write it this way, shorthand. Right? 1 minus delta plus I beta. Okay? Does anyone want to comment on that? No. Okay. So, well, this is just saying the same thing. That formula that we were looking at, if you're in the visible region, you're sort of over here someplace with a refractive index of 1.5, and then you go past the resonances and you get on the other side, and eventually when you come to the X-ray, when you're above the resonances, you're on the negative side and you're flattening out. And this could be a pretty small difference. Okay? In terms of these atomic scattering factors, this is the real part. This is the refractive part, and this is the absorptive part. Okay? F1 and F2, this one is related to delta, this one is related to beta, the absorptive part. Okay? For silicon, this is for silicon, these are, Z equals 14. The refractive part at high enough frequency, this levels off at 14. It's basically saying that at high enough X-ray frequency, the electric field of associated with the X-rays is so rapid that the binding energy of the electrons, all of the electrons in the atom, just doesn't matter. It's just such a high frequency that it's acting as if it's 14 free electrons. Okay? It's also at such a high frequency there's not much absorption. So when you get up around 10 kilovolts, your absorption is dropping like a rock. So if you look up these curves for aluminum, you'd see them dropping like that. This is just, how do you calculate reflectivity? This is a Maxwell's equation thing, which you may or may not be familiar with. But if you do a calculation of reflectivity from some surface at some angle, but at some wavelength, okay, you'll get a formula that looks like this. It looks like it depends on the refractive index and the angle of incidence, okay? And this is the same formula that you would get for radio waves or light waves or X-rays. The formula is the same. It's a matter of what do you put in for n, the refractive index. If you put in this formula and you look at normal incidence, you'll get that the reflectivity at normal incidence is this, delta squared plus beta squared. Well, delta and beta are very small quantities. Here's an example of nickel at 300 eV. This is delta, and this is beta. And when you square it, you've got 10 to the minus 2 squared, 10 to the minus 4. Basically, you're getting very little reflection. And at harder X-rays, these values for delta get even smaller. So the normal incidence reflection is just not much. Okay? What's important, however, is that at glancing incidence, you can get a really strong reflection. And how am I doing on time? Does someone, when are we supposed to end? We started at 8. Oh, we still have time. But anyway, somebody look it up and tell me. So here's how you calculate reflection in general. For radiation incident, it depends on the polarization in the plane or out of the plane. But if you have radiation coming in at some angle, and this is the normal, there'll be radiation that penetrates and light that reflects. The light that reflects is at the same angle. The light going in is normally bent towards the normal. So visible light with refractive index 1.5 greater than 1, this light bends towards the normal. That's what we're used to. But for X-rays, because the refractive index is 1 minus something, it bends away from the normal. If you analyze this, you get what's called Snell's law. Snell's law you probably learned about in high school. So again, we just have to put in a different n, okay? But basically what happens now is you can see that there's a bending here. So as you bring this up to an angle which is close to glancing, okay, when this angle becomes very small, a degree or something like that, this ray is actually running along the surface. And rather than have a wave that goes in and gets absorbed, now almost all of the energy is going to wind up in this wave. This wave will be running along the surface. It's what's called an evanescent wave. There's a certain penetration into the material, but not very much, and you can get a very good reflection. So the question for us is, okay, what angle, how small does this angle have to be to get total external reflection? So we're going to see that. We're going to plug in this refractive index. I'm going to leave off the beta for now just to make the calculation simple. Then we'll see what happens numerically. You can do this. So if you put in 1 minus delta up here, there's a few algebraic steps, but since we're short on time, why don't you just accept that fact that when you put this refractive index in, this equation starts to look like this. And what I want to know is when this is pi over 2. So when this is pi over 2, okay, and this is 1 minus delta, you follow this down and you get that this angle, when this is pi over 2, this angle we call the critical angle, okay? And if you just follow through a few algebraic steps, you get it that it's square root of 2 delta. So if delta was 1 part in 100, square root would be 1 part in 10, something. So here's an example. This is for gold at 1 kilovolt. You can look up at that website I told you about and find out what delta is. And you put that in. So for gold at 1 kilovolt, the critical angle is 3.7, which means that if you come in, let's say, at 2 degrees, you'll be inside the critical angle and you'll get total reflectivity, okay? And you'll get a reflectivity curve. This is for the this is versus angle. You'll get something that approximates this. Inside that angle, you get a very high reflection. For larger angles, you get nothing. Okay? So that's called total external reflection. So again, for instance, the difference, let's go back to our experience with visible light, okay? Visible light, we have total internal reflection. I'm sorry. For visible light, we have total internal reflection. We use it in prisms to turn laser beams by having a reflection inside the crystal. But a more common one would be, suppose you're in a swimming pool, okay? If you look straight up, you put your head underwater, open your eyes. If you look straight up, you can see the clouds. But if you look on an angle, you can't see out. You have total internal reflection. All you see is the dangling legs of other people in the pool, and you don't see out. So there's a total internal reflection for visible light in water or glass or anything like that. For X-rays, there's total external reflection. It's on the outside, okay? So this is why the KB mirror pair works, okay? Yeah.
You're commenting this because as a way to lead the X-rays to the instrument.
Yes.
Right? But does it make sense to do reflectometry with hard X-rays?
I'm sorry, does it make sense to what?
To do reflectometry, to use it to study the material.
Yeah, people do this. They do it, but the most common thing is just to get the X-rays into your material and see what comes through. But for instance, do people use this measurement of the angle of reflectivity?
I mean, this for hard X-rays.
You know, hard X-rays, absolutely. I'm not sure I'm answering your question, but we use this for hard. The KB optics, as you'll see, we use on all hard X-ray beam lines. Not all, but most have them.
But I don't mean the optics, but the reflectivity in synchrotrons as a technique to study, let's say, films or biological membranes.
I imagine we do, but I don't actually know that we do.
Can I elaborate?
Yeah, please, go.
I think they do it like in situ, where they spotter an inorganic film, and they can follow in situ what happens by doing this. Sometimes grazing incident, sometimes reflectometry.
Yeah, okay, yeah. Okay, oh, how much time do we have? You look, yes, I'm sorry, there's a question.
Actually, I just had, if people wanted a non-material science example of reflectivity, there's a lot of study of liquid interfaces, for example, with polymers or proteins on a liquid interface, and then you use the reflectivity to study the film of the biomolecule.
I see.
So it's actually widely used also with hard X-rays.
Okay, great, thank you very much.
You got 35 minutes.
35 minutes, oh great. I'm sorry?
Up to 10:25.
Great. Okay, so here are some curves versus photon energies of reflection. These are from astronomy. I'll show you an example in a moment. But for instance, here's a nickel mirror. This line here is showing that up to photon energies where there's a nickel absorption edge, okay, so just 900 eV, this mirror works very, very well at glancing at this angle, okay? For a slightly larger angle, which would get you out a little bit further, you could use gold, different angle, and here's iridium. Iridium gets you out here to 10 kilovolt. So astronomers use these, they do imaging, they make a telescope with some glancing incidence optics, and by having different mirrors on their satellite with different angles of incidence, they can image different parts of the spectrum. So with using a telescope that has these coatings on the surface, they could image out, let's say, to 10 kilovolts. They could have a different one that's doing this. So for one thing, they could look at an object and they can get a temperature, a rough idea of the temperature by how much energy is being reflected at these different photon energies. This is the KB again. And the KB, by the way, all of these mirrors work as ellipses. So it's best if this shape is an ellipse. An ellipse is a point-to-point focusing. So that would be the best scheme to use. So you might want to use two ellipses.
Sorry, we have time to gain 30. You don't need to rush. I think there was. We have time to gain 30.
Yes.
You don't need to rush.
Oh, okay, thank you. I should slow down. Okay, so you want to use these in elliptical surfaces. So until maybe 5 or 10 years ago, it was difficult to make ellipses. You could make an ellipse, but it wouldn't have a smooth surface, and so you get a lot of scattering. You wouldn't get a nice performance, okay? And so what people knew how to polish was flats. They could make nice flats, and they could make nice spheres. But using, for instance, with your KB pair of mirrors, if they're both spherical, you get some astigmatism and other things, and some aberrations in your optical system. But rather recently, this professor at Osaka University, Yamauchi-san, he and his group came up with a way to polish mirrors of any shape you want, okay? And they use them. They mostly use them at Spring 8, south of Osaka. But now they made a little company called JTEC. And their mirrors are used here at ESRF. They're used at every advanced synchrotron and every advanced FEL. Everybody buys their optics from this company. And I'll show you an example in a moment. This is an early one where there was bending magnet radiation coming down 2 mirrors, focused it onto a sample. The photon energy is high enough, I think it was around 6 kilovolts in the first experiments, that it knocks out core electrons from whatever atoms are in there. So let's say you have a sample with a lot of different atoms in there. You're not, okay? The incident photon is always knocking out core electrons, and then there's a fluorescence. When the electrons drop down, they throw out photons, and so you can look and you can collect this radiation, and you can figure out what's here. And it's very efficient. It's photon in and photon out, so there's no bremsstrahlung, there's no background. So your noise is just counting noise, and you can collect parts per billion of signal. So we use this at the Advanced Light Source. They spent a lot of money to build the ALS. I think it was in US dollars at the time. It was like $100 million, but there was no money for beamlines. That was going to come next year. But they just spent $100 million, and so people are feeling a little sensitive. Could we get some results? So we were asked to quickly put together a beamline that could be used for a couple of different fields, just get some results. So we made a bending magnet. That was easy. It's already part of this thing. A simple KB mirror pair, okay, focused here to look at fluorescence, and all kinds of people use this. But one of the early ones was a company that makes solar cells. And solar cells is their only product, and it's supposed to generate some voltage and current. And there was a company in Ohio. It's not too close to California, but the only product they make, and all of a sudden their solar cells aren't working. Something's gone wrong, they don't know what. And someone told them, well, you could bring it to Berkeley, and they did. And because it's high enough photon energy, it's not in vacuum or anything. You just put your sample there and look at the fluorescence yields. And this is what they saw. This is looking at fluorescence from iron. There were iron spikes in there. There's not supposed to be any iron in their solar cell. And there were all these spikes of emission. So it was clear that that's what their problem was. They have iron in their solar cell. Please, you can just go home. So they came and went in a single day, had their data. We'll go look for the iron. And they were gone, and that was good. And there were all kinds of other experiments. But in this case, these were not elliptical mirrors. And the focal spot was, I forget, a few microns. Okay? The newer experiments, this is from Yamauchi's group at Spring 8, and they're down to here 30 nanometers in the 2 directions. They can actually get below 10 nanometers in both directions. So basically they hold the world's record. This is a few years old by this time. The students are getting professorships at different places and good jobs in different places. So that was a big result. And this is not the best example, but it just shows this is single cell probing. So they're using this focus of around 30 nanometers to probe spatially within a single cell and look at the fluorescent emission and seeing the different elements that exist and where they exist. So it's not the highest resolution in the world, but it's down. So now they do this down around below 10 nanometers, I think 7 or 8 nanometers. And so this is using elliptical KB optics. They are also planning to use their optics with the free electron laser to focus this gigawatts of power into the smallest possible spots. And they are hoping to do new physics of what happens when you have such an amount of power into a small spot. So switching fields, so that was reflective optics. That was total external reflection optics. This is what happens when you make alternate coatings of a particular material. You notice these are nice and flat. The black is the molybdenum in this case. The whitish is silicon. At the photon energies that are going to be used here, which are below the silicon L edge, the silicon is not absorbing because these photons don't have enough energy to be absorbed. They can't kick out an electron. So the white is almost like vacuum in this case. And the molybdenum itself has interesting properties. So at any rate, this mirror, not what I wanted to show you. This mirror, it's courtesy of Sascha Beit. She's now in Hamburg. She was in California at the time she did this. She got a measurement of normal incidence reflectivity of about 70%. So it was startling at the time. Okay, it's a kind of unique thing. It only works at these relatively low photon energies, and it's got to be precisely matched. There's a Bragg condition. So depending on the angle of incidence, there's a Bragg condition here, but amorphous within the layers. And you might be interested that Sascha made this measurement about a week before she had a baby. Yeah, little Katerina. So little Katerina is not so little anymore, but this is an example of normal incidence reflectivity, the same kind of coatings used on a telescope to look at the emission lines of iron that's been ionized 10 times in the sun. And so this is basically an X-ray image of a big solar flare. Okay? The Earth would be a little tiny thing up here on the same scale. So there's a lot of work that's done in astronomy and astrophysics using these same reflective optics, sometimes with multi-layer coating, sometimes just glancing incidence, generally with mirrored pairs, not always KB. This is a so-called Whirlpool Galaxy. This is a combination picture of X-rays and ultraviolet, but kind of thing I thought might be interesting to you. So we've spoken about reflective optics, total external, and we've talked a little bit about multi-layer coatings. The multi-layer coatings only work at those at normal incidence in that low energies, the 90 EV or 80 EV. But at glancing incidence or other angles, they work quite well. So we use multi-layer coatings both for hard X-rays and for soft X-rays, but not at normal incidence. We have to use them at some other angle. Okay. So here's what we call zone plates. This is a zone plate lens, okay, which can be used, in this case, the zone plate lens is used to focus radiation into a small spot in a microscope called a scanning microscope, and then the sample is raster scanned in front of the pinhole, okay, or aperture really, and what you measure is just how much flux is getting through. So as a function of position, you measure how much flux is there, and then you learn about the absorption in the material. And this is called a scanning microscope or scanning transmission X-ray microscope. Okay? They typically get resolutions of between 10 and 20 nanometers. Okay? This one, by the way, in order to get the lens is imaging the source. A lens images one plane to another plane, right? So this lens is imaging the undulator radiation onto the sample. To get the smallest possible spot here, the spot back here has to appear to be a point source, right? You need a spherical wave or near a plane wave incident on this lens to get the smallest spot here. So to get a spherical wave here, you had to put a pinhole in front of your undulator beam. Okay? If you didn't, you use the full beam, the only thing that would happen would be the spot size would be bigger, your resolution would be a little compromised. So for scanning microscopes, if you see one here at ESRF, they certainly have them, they will be using a pinhole aperture upstream, and they'll be getting spatially coherent radiation. A different microscope I call the full field microscope, and you can use bending magnet. It doesn't require the spatial coherence of the radiation, and you'll have some backlighting. It looks like your high school microscope turned up this way, and this would be a high magnification. These would be close, this would be far away, but just imagine this is, you backlight your sample, you have a lens, and you project an image back maybe into your eye, okay, for a simple biological microscope. Well, you do the same with X-rays here. You can use bending magnet or undulator radiation, illuminate your sample. The radiation comes through, but it's diffracted, so small feature sizes spread the radiation, and then that gets imaged here, and it also gets about the same resolution. Okay? So I'm going to show you an example, I think, from each one of those. First I'll show you, how does this work as a lens? Why does this work as a lens? This is what one looks like. This is from Stanford, from the group led by Ann Sekdinawat. Ann is the co-author on the book, which I gave you chapters from. Okay, you can see where the outer zones are getting narrow. The inner zones are a little bit broader, period. And these are deep. These are made for X-rays. These are made for use at 5 or 10 keV. Mostly zone plates have been used for soft X-rays until recently. Not made for hard X-rays, because for hard X-rays they needed to be thicker. And it's hard to get both thick and narrow. It's called the aspect ratio.
What size are these?
Oh yeah, thanks. What size are these things? A typical zone plate, one of these giant zone plates, is about the size of a human hair. So like 50 or 100 microns in diameter, and the outer zones would be a certain number of nanometers, 10 nanometers. It basically sets the resolution. How small is that outer zone? There's a little numerical factor, it depends on illumination, but basically the outer zone width would be 10 or 20 nanometers, and the total diameter would be 50, 100 microns, could be 30 microns. So yeah, so you're a long way from that undulator, but actually alignment is not a big problem.
I want to ask, what's the size of the X-ray mirror? Because like since the critical angle is very small and your beam has like a size, so that's like your mirror need to be like very long to like need a long surface to.
Yeah. So.
I think it's like larger than the normal like optic mirror.
Right. So for the glancing incidence reflection, for instance, the light comes out of the undulator and you're going to deflect it into the microscope end station. Somebody else is doing a different experiment. That mirror, because the angle is so small, that mirror winds up being quite long. You know, a foot, a couple of feet, half a meter long, something like that. Okay? Because you're at glancing incidence and your beam is only so many microradians, you're really stretching it out. So that's for the reflective mirror. This thing is going to be at normal incidence. Okay, so after the bounce off the mirror, that radiation, when in that cone, is going to illuminate this object, this zone plate, and the diameter of about 100 microns is kind of what you can get. Sometimes you put some curvature on the mirror to focus it a little bit. Okay, so that's what one looks like. Again, so we were talking before about, you probably learned about this in high school. This is a transmission grating where these are opaque, the radiation comes through, and the light that got through here, some of it goes straight ahead. But some goes to this order or this order, and in fact to other orders. And for the radiation from each of these openings to add in phase, you want to add on this one and this one. This one should be one wavelength longer. And so if you say, okay, I just made this thing here, you want to add for every space here, that's this is D, this is one period, you want some angle, you want this to add one wavelength. that will give you coherent addition. Okay? And so if you just use the, your trig, you'll find that the sine of the angle is lambda over d. The sine of this angle is lambda over d. Okay? And you can have higher orders where you don't add one wavelength, but you add 3 or 5 wavelengths. And that's what the m is about. Okay? So you get different orders. If you calculate how much energy goes into 0th and plus and minus 1, you find out something like this. This is the efficiency into the different orders. For m equals 1, it's about, each of these is about 1 over pi squared. So this works like a lens. This is a grating. I'm sorry, I'll get to the lens in a moment. But basically, you're getting about 1%. I'm sorry, you're getting about 10%, pi squared. You're getting 10% this way and 10% this way. Okay? So now, oops. So now if we talk about, okay, how does a zone plate work as a lens? You have the same grating equation, okay? And you're going to get 10%, you get some of it just comes straight through, some of it comes into focus, and some of it goes defocus, okay? So about 10% of the light will come into this, and you can get a real, you could ask yourself, well, how can I get, what distance, what focal length should I go to in order to get the radiation from all of these openings to come to a focus? So basically, you do the same thing you did for the transmission grating, and you apply the Pythagorean formula. This is a right triangle. Each of these is a right triangle. This is one leg. The radius is another leg. And this is the hypotenuse. And the hypotenuse is always adding half wavelengths. But we block the ones that would be destructive interference. So we're only interested in the ones where we add a wavelength. But if you use the Pythagorean formula here, the unknown focal distance yet, we're going to find it out, f squared plus the radius squared equals the hypotenuse squared. And if you just expand this out and go through the algebra, you'll find that the various radii follow this simple formula. Okay? So as you go out and larger, as this angle gets larger and larger, it's a square root, depends on wavelength and f. And so this is telling you it's a prescription for how you should write this pattern. So if you write that pattern, a zone plate pattern, you'll produce a structure that will have a real first order focus. And about 10% of the light will be in the first order focus. And when I say 10%, that's because these zones are opaque. At hard X-ray wavelengths, you don't have to block them. These are blocked because we don't want the half wavelengths which are destructive interference, right? So we blocked half of the zones, and we only allowed the constructive one for the alternate zones. But in hard X-rays, you actually don't have to block them. You can get a phase reversal. There isn't so much absorption, and there is a phase, there is a refractive index, that 1 minus delta, and you can get the radiation coming through this material to have almost a pi phase shift. Okay? Some questions about that?
How do you do that?
Well, when X-rays come through some material, solid material, there's absorption. We could calculate that. But there was also a phase shift. There was a 1 minus delta, and so there was a changing of the phase velocity going through the material. And if you play it right, you can get a phase reversal so that the thickness just gets you a 180-degree phase. So light coming through this one is just vacuum, but the next one could be a phase reversal. So 180 degrees would be perfect, but you can live with some partial effect. Okay? So when I said this was 10%, that was with opaque structures, is what we do in the soft X-ray. For the hard X-ray regime, they can get 30 or 40% into this regime. Okay, so now how do we use these things? Oh, you can also use them from point-to-point focusing. You just apply the Pythagorean formula not only on this side, but on this side for the point-to-point focusing. And if you combine those two equations, you'll find you get a sort of a lens equation. 1 over the image distance plus 1 over the object distance equals 1 over the focal length. So this thing works as a lens in all the ways. It works for depth of focus also. The only thing is it has an absorption issue. Okay? But except for the absorption, it works like a real lens, except it works on diffraction rather than on refraction. This is just saying that there is a depth of focus with any lens, and this one has the same lens, and it just depends on the numerical aperture. What is the depth of focus? Just depends on the numerical aperture, meaning the half angle here. Yeah?
You said that this kind of lens can also be used for wide field, large field microscopy?
Somewhat. The lens itself is only maybe 100 microns in diameter, so you're not going to use it to look at a millimeter object. But if you're looking at some biological structures, for instance, I'm going to show you a CT scan in a moment of a single cell, it works.
I was wondering how big is the spherical aberration of this kind of object?
Yes, it's an issue, but you can still get resolutions of 10 to 20 nanometers. So the best performance is in the center of the object, you know. So maybe the first 10 microns, but that's about the size of a cell. This is just some parameters. This is how the full field microscope might work on a bending magnet. You could use an undulator. In fact, I'm going to show you an image later. There's a plane mirror to glancing incidence, a condenser zone plate, okay, to bring the radiation onto your sample, and then a microzone plate at a high magnification of a few thousand. Image this onto your CCD detector, and you see it. These things are generally indexed in the holder so that when the biologist comes into the lab, they put their sample in the visible light microscope, which may have fluorescence and other features. And basically, when they search around, they're looking at thousands of cells, and they pick out some which look healthy and some which look a little odd. And then they just note, there'll be a computer here, and they'll note what the coordinates were. And then with these index markings, they stick it into the microscope, and it starts clicking, and you can get thousands of images in an 8-hour run. Okay. What kind of resolution can you get using a test pattern? This is showing lines and spaces. It's a thin cut of a multi-layer mirror, and the resolution here was the measurement was at 15 nanometer lines and spaces could be seen quite well. So this was a PhD thesis for Wei-Lun Chao. The spatial resolution, the record at the time, this is a few years ago, was something like 25 microns, 25 nanometers. And we told Wei-Lun that if you could get down to 20 nanometers, you're done. And so he got down to 15 nanometers. Actually, a little bit better than that, 13 nanometers. So this is a nice, clear image. And this is what happens if you try to push it to even higher resolution, you see nothing. So I've been telling you about a zone plate microscope was this guy here, but this was another PhD thesis. This was Anne Sakdinawat. She's the co-author on the book, and she heads a group at Stanford now called NanoX, which makes zone plates and all kinds of other structures. But in her PhD thesis, she got the idea to combine a normal zone plate with some angular pattern. So actually, these are all dual functions. All of these zone plates have the function that they can image or focus the radiation, but they do something in addition. These two add angular momentum. So for instance, if you're studying magnetic materials and you want to see transitions in the magnetic materials, you need some degree of angular momentum to get the transition in order to satisfy the quantum rules for the transition. So these are two different amounts of angular momentum being added. This is differential interference contrast, DIC. This rather weird one has a third order put into the zone, so it really looks weird. It kind of screws up the resolution, But because the resolution isn't so good, it has an increased depth of field by the square. And since Anne knows what aberration she put into this, she can then go back plane by plane and correct and get back the resolution that would be set by the outer zone, but over a much bigger depth of field. So this was used to increase depth of field. So for instance, you'll see some images in a moment of a biological microscopy of a single cell, a CT scan, and the CT scan is limited in resolution not by the usual property of the lens, but because the cell is too thick for the depth of field. Okay? So this was a partial solution to that. And I would say that in her group now, they have some zone plates which are far more complicated than this. They're just incredible. They use them for tychography, if you know what tychography is. I guess we blew that. So I'll show you some images. So in the biological microscopy now, if you try to make an X-ray image of a single cell, you'll simply destroy it. Okay? So you have to do a quick cryo freeze so that even though you're breaking bonds by the X-rays, the parts don't move around. Okay? So you need to do that. And if you do that, you can rotate the sample in front of the microscope. So there's the light coming in, and if you rotate the sample and keep producing images, you get something like this. This is okay, so the sample's going to rotate. Why isn't, well, I was going to show you a rotation there, but here's similar work. Actually, same person doing it. This is the work led by Gerd Schneider at Bessie and the biologist James McNally of the U.S. National Institutes of Health. And they're looking at a mouse cell, as I recall. This is the cell. This is a 2D image, but it came from making many 2D images in which you rotate the sample. And every 1 degree, you take another image. So it's like a CT scan. So if you have a bicycle accident yourself and you go to the hospital, they put you in the CT scanner, this long tube, and they rotate the X-rays around you, and they keep taking a lot of images, and then they use computer-aided tomography to reconstruct all of that into a 3D image of everything inside your brain. Okay? So this is going to be a CT image of a single cell, and you're going to see focusing through the cell. So here's a single 2D image of this cell. Okay, the resolution is of order 25 nanometers. Actually, it's a little bit more than that, 30 nanometers or something. Okay, this is the cell. Some mitochondria, endoplasmic reticulum, some vesicles here that are used to carry proteins. The nucleus is here, and this is the nuclear membrane. It's a double membrane, double wall membrane. We hadn't seen this before in an X-ray microscope. This is the first time we saw that. And here you can see you're changing focus through this cell. So it's like a 10 micron thick cell, and you're seeing some vesicles coming into focus and out of focus as you're seeing different parts. So you've got this cell, and you're looking at different planes within the cell. And let me see if I. So there you can see the ER disappearing, and some vesicles. And the darker they are, the more protein they have. Okay. Okay. So that's an example then of zone plates, how they work, and what they're used for. This same microscope for people interested in material science. These are titanium-containing fibers that are also seen in this microscope, and they're analyzed spectroscopically. So there's a crystal monochromator here, and they're using this to see what are these titanium wires, fibers, and how their spectral content response depends on the fineness, how thin these fibers are, and even what's their orientation because of the electric field. This is the scanning microscope, the scanning transmission. So again, you'd put an undulator upstream with a pinhole to produce a spherical wavefront. The zone plate would focus it down to a spot size of about 10 nanometers on the sample, and then you raster scan the sample back and forth, up and down, and you record this. This is not a pinhole for coherence. It's just that, remember that there was straight through X-rays. This is the focus X-ray, but there was also straight through X-rays and divergent X-rays, and this is an aperture which is big enough to allow this radiation to come through and block the others. Okay? And this, often they use this in spectroscopic examples. There's less radiation damage with this microscope than there was with the previous one, because the inefficiency of the lens is upstream before the sample. So for soft matter, environmental work, environmental studies, this is the preferred microscope. And they'll change the monochromator setting and keep making different images for different photon energies, and they'll get results like this. So this is some biological material from the Saskatoon River, and they're looking at a certain part, and I think here they're looking at the iron edge and how the iron edge looks a little different depending on where you are in the sample, and it's because of the local environment of those iron atoms. In different places in the cell, the binding to their neighbors is a little different, and so they use this as a tool, spectroscopic environmental science tool. So they're combining both photon energy, so they're getting spectroscopy, but it's spatially resolved spectroscopy. Okay? So that's a second example of using zone plates. Here, this is at ESRF. This is work of Marina Cote. I don't know if you see her, if you're visiting her. I had lunch with her yesterday. And they have a microscope here. They have a system here of imaging. So they have an undulator, a double crystal monochromator. They can put a zone plate in or not put a zone plate in. They can look at diffraction, if they put a diffraction camera in place, and they can look at spectroscopy. And so they have all of these different things. Possibility, this is some work from a few years ago from Marina, and this was looking at an Egyptian vase which has a beautiful characteristic blue in it, actually, and it's called Egyptian blue, right? And if you look into it, you'll find there's a Cambodian blue, there's a Turkish blue. So different cultures discovered how to make blues which didn't fade. And they don't fade because it's not a chemical thing. It's what elements, it is a chemical thing, it's what elements, stable elements are used. And it turns out that what was learned in this analysis was that by the museum allowed Marina to take a little tiny speck of something of order 100 microns and do spectroscopy on it and compare the spectroscopy of that little fragment with absorption spectra that they make a library of. So for instance, this is sulfur and chlorine. This is different versions of sulfur and different versions of molecules with chlorine in it, and they all have certain features to it, spectroscopic features or fingerprints, spectroscopic fingerprints. And it was, am I going to wrong? That's what was used to identify which elements were responsible for this blue color. Okay? So she does a whole study of, what do they call it? Basically, cultural heritage. So it's not only paintings, it's not only vases, but paintings, what's behind one painting, what kind of walls, what materials were walls made out of. They do all kinds of environmental studies here at this particular beamline. And then I just wanted to say that not everything uses lenses. There is some lensless imaging. I'll show you two versions of lensless imaging. This is from Marco Stampanoni's group at the Swiss light source, where they use a bending magnet, but it's a super bend. It has a strong bending magnet radiation to get more photon flux, and they use a double crystal monochromator. So the radiation is in this small angle, so many microradians, and then there's no optic. They simply take their object and rotate it in front of it and record that on a so-called scintillator. A scintillator is a material with X-rays coming in the front and visible light going out the back. So the resolution winds up being visible light limited. The resolution, there'll be a microscope behind here. The resolution will be about a micron, okay? But they can look at objects, and there's lots of science that can be done at a micron. And so, and this is showing that they're, for instance, maybe 20 keV or something like that. And this is an interesting example. These are embryos, fossilized embryos that were discovered in China. Maybe 10 years ago, there was this discovery in the desert, a very dry place where these things were basically desiccated, and so not destroyed. And they're only like a millimeter in diameter, and so it's an embryo. It's the beginning of life, and the period that they came from was just when there was an explosion of life forms. So they're very interesting to people, and they would love to know what the structure looks like inside this embryo. But these, if you just touch them, they're like powder. They're gone. Okay, so they needed a non-destructive method with a resolution of order a micron. These are maybe a millimeter or a half millimeter in diameter, and they want to rotate this thing and get it. And so they used the technique that I just showed you, lensless imaging. Here's some of the parameters, okay? And they were able, and actually, they were able to get the front cover of Nature magazine also. So this was a big plus for their research group. So that's an example of lensless imaging. This is also lensless imaging at the same group. This is looking at a part of a mouse brain, and this is the structure for blood flow. Okay, what they call the microvascular structure of showing where blood flow can go in a mouse brain. So they now actually do clinical, the group does most of their work, I think, at the synchrotron, but they also use laboratory sources, and they're working on many kilovolt X-ray imaging in clinical environment. So they're trying to develop instrumentation for medical purposes, and so they're pretty well along the way on that. Then there's lensless imaging where you use coherent light. That was lensless imaging with just projection, just shadow casting. This is a case, this is lensless coherent diffractive imaging, CDI. You'll hear other names for it, but it's all CDI, where you either use a free electron laser or you use spatially filtered, put a pinhole in front of an undulator, launch a spherical wave, which is almost planar, onto your object, and you look at a diffraction pattern and you record the diffraction pattern. And then you need to take that, you have to process that information. And the way it's done is with a computational technique. So I'm going to leave that for other speakers. I know you have some people who are going to tell you about this lensless imaging and how they take this diffraction pattern and iterate computationally to reconstruct what the object must have been like. Okay? Because in the diffraction pattern, you don't actually have an image there. You have a bunch of spots. Okay? And you don't have phase associated with that. So you can't simply back project it and get the object. You only recorded intensities, not electric fields. So you need to go through this iterative process, and that's what's this coherent diffractive imaging. And there's a related technique of tychography in which you do this and you rotate the object. This is an early example of that CDI. This was by Marcassini and Chapman. It was a big group. And these were a bunch of 50 nanometer gold spheres mounted on a thin film. So it looked like a three-dimensional structure. And they rotate this. They rotated it, and they did CDI. And these are reconstructed images. So they were able to reconstruct, even though they didn't have the phase and they didn't have a lens, they were able to see these 50 nanometer gold spheres. And so now people are trying to push that into the nanometer regime. Yeah, so for instance, this is work that's done on the free electron laser. The pulses are short, femtoseconds, protein nanocrystallography. So that's a hot field. And it's a challenging field. It's a giant challenge of how, so currently they're not at the nanometer scale, they're much larger scale. And the data collection takes a lot of time, actually. Well, maybe this is an example of some recent work. So this is the recorded diffraction pattern. This is the reconstructed image, okay, for different objects. These are all different objects. This is with a free electron laser. And you can see what the spatial scale is. They're resolved to, at this point, 100 nanometers. So that was a few years ago, 2015, so it's getting better. What do I want to tell you? I told you that in this tychography and CDI, the data collection times are kind of long. So with the new free electron, with the new synchrotrons, this long elliptical beam that I've been telling you about, the electron beam is 100 times wider than it is high. The new rings are trying to get to, if not to a circle, something close to a circle. And in the present situation, when you're trying to do coherent imaging, you wind up, this is 100 times wider, so you wind up taking one part in 100 and throwing away 99 out of 100. So if you can take this radiation and collapse it and produce it in a little circle, you can get 100 times more flux. So the new rings that are coming up are going to get actually more than 100 times. In the ALS, they're expecting to get 1,000 times more coherent photon flux. So these kinds of CDI and tychography are going to benefit the most. Actually, all imaging experiments are going to gain by a factor of several hundred in reduced exposure time. So we have 8 minutes, and I can tell you about this computer chip business that I have hinted at. So until now, computer chips are made in recent years with 193 nanometer laser light. It's used to copy over and over again some electronic pattern with very small feature sizes. And by what's called Moore's law, after Gordon Moore, every 2 or 3 years, the patterns get smaller and smaller and smaller, which makes them able to store more information and make their calculations faster. So this is what's called Moore's law. But Moore's law has been going on for like 30 years, and it's over the last 5 years it just leveled off. It wasn't going. There was no more improvements in this, and so there's a technique of not using refractive focusing, like 193, or imaging, I should say, not replicating the electronic pattern with visible or ultraviolet light. The 193 is in the ultraviolet region. And so they're always making the wavelength shorter, shorter, shorter to see smaller and smaller features. But when you try to go beyond 193 in the ultraviolet, absorption suddenly wipes you out. Whoops. Absorption wipes you out, and you can't go any further. So the proposal was made in 1986 by a Japanese scientist named Hiro Kinoshita. Kinoshita-san proposed that you could use these reflective coatings, these polysilicon reflection coatings, which get to 70%. You could actually go from refractive optics to reflective optics and using a much shorter wavelength. So going from 193 nanometers jump to 13 nanometers, which is this 92 EV just below the silicon L edge in the multilayer. And you could make an optical system that worked on reflection. Okay? Each of the mirrors, it takes a lot of mirrors in any event, whether you're using ultraviolet or not. There are so many mirrors, and they're all 70% reflectivity. If you take, there's like 11 mirrors or 12 mirrors here, 0.7 to the 11th is not good. It means that you're going to need a lot of power to produce the EUV radiation, more than you had needed recently. And that held up this project for a long time, more than 10 years. So, the way it works is it's called a step and scan. This thing is about the size from that wall to that wall, this ceiling equal. It's like a small bus. They cost 130 million each, okay? And they produce about 30 or 40 per year. They're made by a Dutch company called ASM Lithography, ASML. And they use this reflective optical scheme. And this would be a wafer. It'd be something like this, silicon wafer. And they print all of these electronic patterns. They just print it over and over and over, and then they slice them up later. And the way it works is it's a step and scan. They do one, and they scan the image here. So there's a mask that has a pattern on it that's going to be copied onto the wafer. One goes one way, one comes the other way. And you print these patterns over and over again. So sometimes it's called a scanner, and sometimes it's called step and scan. But it was held up for about 10 years because there wasn't enough power to overcome all of those reflective losses. But there was big progress in 2017. In January, a company in Taiwan called the Taiwan Semiconductor Manufacturing Company, TSMC, took it from 9 watts of power to 90 watts of power, and a few months later they got up to 200 or 250, but that was it. So there was an announcement from TSMC and ASML that the power had jumped from 9 watts to 90 watts. That was in February 2017. In April there was an announcement by ASML that some big customer that they couldn't name, but it was Intel, had just bought up everything they could make for the next year. It's 30 units at 130 million each. It was $1 billion announcement. And they started, and it's using these coatings. And it was a breakthrough. It was the EU. So people thought that Moore's law was dead. Okay, in general, I don't think the general public knew that Moore's law was dead, but the scientists and engineers knew it was dead. And for instance, in my first book, there's a chapter on EUV lithography. The second book, when I've given you chapters for, there's no chapter on lithography. It was dead, okay? Fortunately, some friends here in Europe convinced us, just as we went to press, that that was a mistake. We should have, even though we didn't know about the source breakthrough yet, I guess it was just happening as we went to press. We added a few pages in a few different chapters, one on imaging and one was on the plasma source. But anyway, there was this big breakthrough, and now computer chips, the latest versions of high-tech computer chips are now made in part with EUV. So each computer chip will have like 20 layers. And a few layers will be the ones that are the most advanced for the fastest calculations, et cetera. So the newest smartphones that you could buy from Samsung or Apple, for instance, that were just announced at the end of 2019, use this EUV. And these are just announcements that were coming out in the end of 2018 that they were coming. And this is just some blurb, but basically this is about the Apple iPhone 11 now uses EUV. And I'm told by the people at ASML who make these units is that the Samsung is the best, is the most advanced. I think it's called the Samsung Galaxy 10 or something like that, is the most advanced cell phone you can get now, and it's going to appear in all kinds of products. So it's not exactly X-rays, but it's everything that you do it's pretty much the same business. So we are done. Yay. Oh, I'm going to be at the cafeteria, I guess around lunchtime. So if anyone has more questions, you can find me there. Okay. Any questions before we end? Okay. Okay, you're not allowed to applause. It's forbidden. Okay. So we're over. I'm glad to have met you all. You can send me email. You look for those chapters that I told you about to see if any of the reading helps. And if there's something, I couldn't put every chapter there. I don't think Cambridge would have liked that. But if any of you want some other chapters, just tell me by email and I'll send them to you. Okay, maybe see you in the cafeteria.